One of the last teams lost in blue styrofoam with OSM 4F written on it on the airfields. Can the team come and get it, please? At the unloading area, sorry.
In preparation, please, Team Locreum 24. Paula, are you here? Paula, bitte. Paula. Ah, da. Was braucht ihr? Braucht ihr sie? Habt ihr die Uhr auf dem Flugfeld? Okay, I'm very sorry to all our YouTube audience. We had a little power outage. Our generator is so silent we didn't hear that it went out, probably 2 hours ago. And now we have team number 26, Wings, flying with their aircraft Moby Dick. And the Takeoff attempt is good. So Harvings is flying, took off within 40 meters, and they have a payload of 0.2 kilograms. I'm very sorry that we had to do a new YouTube live stream. Unfortunately, it was not possible to go forward with the old link. I'm very sorry about that. I call for... No, sorry. Please, Team 24 Locreum, come to the preparation tent. And Team 28, I think, is at the very end. Please come also to the preparation tent. If we're lucky, we make all four remaining flights before the wind's coming and the rain is coming, hopefully.
We used MDF boards while producing our mold for the body. We processed this plate with CNC, made them what we wanted, and produced female molds. CNC technology is the process of giving the desired geometric shape by removing chips of different shape and size from the piece, by referring to the project technical driving of the design workpiece in accordance with the standards. This shaping process should be done by means of suitable tools and benches. We tried to make these processed plates perfect by sanding them with sandpaper. Then we finalized our body using carbon fiber and epoxy with vacuum bagging method. Vacuum bagging is the clamping method that uses atmospheric pressure to hold the epoxy coating components of the laminate in place until the epoxy cures. We also used CNC cutting while producing our body's cover. We used the buses that we previously determined as the material to be used in our wing production. In order to obtain the wing profile, we preferred cutting it with laser cutting in order to provide it.
And we have liftoff. It's a green flag. Flight is good. It's getting altitude. The time is running for 60 seconds now to climb and gain altitude with the payload. This is one of the 3 tasks of the flight. We have 30 seconds remaining for the climb. And in 4 or 5 seconds the distance task will start, where you should cover as much distance with your payload as possible to transport the blood bags to the destination. Let's start it now. There's 2 minutes flights for the distance task. I call again team 28, please. 28 for preparation. We are 1 minute into our distance task. There's 1 minute remaining. He's quite low. There's a minimum altitude of 10 meters that is counted. Or my timing is a little bit off. No, it's through. My calculation, there's still 10 seconds remaining for the distance task. But it seems the pilot is making a safe landing or trying to attempt a safe landing. Next up is Team 29 Wood Aero Design with their aircraft Mosquito. They are taking off within 60 meters and attempting to lift 0.6 kilograms. Little announcement to all competitors: there will probably be some wind shortly and some rain, so prepare. We will halt the competition for now until that rain is gone, and we will make the final 2 flights afterwards. It might probably be half an hour or something like that until the rain is gone. We will see.
Ja, ich mach so, dann fest.
We used MDF boards while producing our mold for the body. We processed this plate with CNC, made them what we wanted, and produced female molds. CNC technology is the process of giving the desired geometric shape by removing chips of different shape and size from the piece, by referring to the project technical driving of the design workpiece in accordance with the standards. This shaping process should be done by means of suitable tools and benches. We try to make these processed plates perfect by sanding them with sandpaper. Then we finalized our body using carbon fiber and epoxy with vacuum bagging method. Vacuum bagging is the clamping method that uses atmospheric pressure to hold the epoxy coating components of the laminate in place until the epoxy cures. We also used CNC cutting while producing our body's cover. We used the buses that we previously determined as the material to be used in our wing production. In order to obtain the wing profile, we preferred cutting it with laser cutting in order to provide a clearer and smoother transition. We combined this profile using glue. At the same time, we wanted to ensure durability by using carbon pipes between the buses we cut. Laser cutting technology is the process based on cutting materials with the help of laser. To put it simply, it is the process of directing a high and powerful laser output to materials to be cut through the automation system. We used hinges when connecting the control surface to the wings. Finally, we supported the aerodynamic flow by covering the wings with wrapping paper. In this cutting process, we used irons produced for this job. These irons stretch the wrapping paper with the help of heat, ensuring that the paper is integrated with the wing skeleton. We produce the internal structure of the tail just as we produce the wings. In addition, we combined our tails consisting of 3 parts with the part we prepared using a 3D printer. We used PAL filament for all the plastic part we produced. We produced a basket of balsa to carry the blood bags. We used aluminum for the landing gear because we believe that this material will be durable during landing. We positioned it to fit this tail dragger configuration and center of gravity. To make a static test, after the wing frame connection was made, a water bottle equal to the weight of the aircraft was placed inside the fuselage. 2 friends from our team lifted the plane into the air by holding it from the ends of the wings. We used hook and loop type while making our placements so that they can be mounted more easily during the competition. We made these settlements based on the center of gravity. Bolts are used to connect the tail, pipe and body. Carbon pipes from the wings are reinforced inside the fuselage with a carbon insert. We produced the box in which the aircraft will be carried out of wood based on the dimensions specified in the regulation.
The thrust test was performed on the stand with a precision scale at the base by starting the engine and reading the power from the scale. Servo motors are connected with power in the middle, ground and signal readings at the other edges. ESC, which enables to control the speed and direction of the motor, was connected to the motor and was connected to the receiver like servo connections. The 2S battery to be used in case of emergency was connected to the receiver as specified in the regulations. The ailerons were controlled from the first and sixth channels of the controller. The elevator was controlled from the second channel, the rudder was controlled from the fourth channel, and the motor was controlled from the third channel.
Ver. Düz yap, sağ yap, biraz sağ yap. Dikme. Daha yumuşak.
Hello, I'm Paweł,
And I'm Grzegorz.
and as the members of the Warsaw University of Technology SIE Aero Design Club, we would like to present to you our air cargo class aircraft, the Mosquito. The plane has a specially designed cargo compartment for blood transport, a carb weight of 2.4 kilograms, and is able to carry a load of 3.2 kilograms. The aircraft has semi-elliptical wing with winglets to minimize induced drag. As the aircraft is going to be operated from a grass airstrip, the wide main landing gear strut is applied. Our team's structure consists of 3 personnel on board: the president, the vice president, and the treasurer. They are responsible for organizing the workspace in the workshop, providing the supplies, contacting with our university authorities and our sponsors. All actions and major decisions have to be consulted with our faculty advisor. Our project routine started with selecting a coordinator who would organize the design, calculation and testing processes. The construction was carried out by the entire association, supervised by the main coordinator and his team, and the responsibility for logistical and financial matters were under conduct of club's leaders. For work organizations, we used apps like Microsoft Teams or Trello.
We started the preliminary design process in September 2021. The manufacturing process was planned for the end of winter because we didn't want to risk COVID lockdown interrupting our work, and first months were spent on designing, calculations and sponsor handling. Unfortunately, the construction of the plane started with a delay due to lack of funds to purchase materials. This was also the first time our club would participate in the Air Cargo Challenge, so this was quite a new challenge for us. Due to manufacturability limitations, we had to keep the balance between self-made and outsourced aircraft elements. Additionally, our own manufacturability capabilities were reduced as some of our tools were stuck overseas after participating in a different competition. Following the competition rules, we outlined the basic aircraft design. Then, scoring analysis allowed us to select the most important parameters, further narrowing down the design.
The rules are strict about motor and propellers, so we started with their selection to determine the available thrust. We tested the purchased motor and propellers in a wind tunnel for various airflow conditions with voltage limits as described in the regulations. Basing on the test results, we have picked cam carbon propeller, which generates slightly higher thrust than the APC. We have considered low wing, high wing and flying wing configurations, and after analyzing the pros and the cons, we have decided to use the high wing because of its high stability. The aim was to design a lightweight aircraft with good access to cargo compartment. The doors are on the right side of the fuselage. The lightweight fuselage was achieved thanks to mounting tail boom and main landing gear to the wing. In the case of deep stall, the classical empennage was selected.
To establish main parameter of our construction, we used a thrust-to-weight plot. The team assumed that the climb rate and the payload mass would be the most optimal scoring categories to achieve. We performed a score computation in MATLAB and came to the conclusion that the optimal climb rate and payload would be 1.8 meter per second and 3.2 kilograms with runway length 60 meters. For the final configuration, we prepared a payload prediction curve considering changes in dynamic, pressure and thrust. At this point, close attention was paid to airfoil selection. To achieve high vertical speed, it was necessary to apply airfoil with high CL3 divided by CD squared ratio. We considered 3 airfoils: Sailing 3024, Sailing 3320 and PP02. Using AVL and XFLR5 software and analytical formulas, we compared them, and basing on data we decided to use PP02 with 10% thickness and 7% camber, which stands out with its high ratio.
The team opted for elliptical wing as according to the Mach law, the elliptical load distribution has the smallest induced drag. To minimize 3D flow behind the wing, the straight trailing edge was applied. To improve the bad stall characteristics of an elliptical wing, we designed a geometrical wing twist, so the flow separation would occur lately at the ailerons. To decrease induced drag further, we decided to use winglets. The goal was to get a proportional distribution of an induced angle to the cosine of the lateral inclination angle. We achieved that through the use of twist and Selic 3010 and 9032 airfoils. Using winging devices allowed us to decrease induced drag by 10% and increase CL cube to CD squared ratio by about 15%. Knowing the density of used materials, we performed the mass and balance analysis. During manufacturing, each part was weighed and compared to our expectations to ensure that they meet the requirements. Thanks to such control, we achieved planned mass. Moreover, the aircraft in empty configuration doesn't need any additional balance.
As we decided to maximize climb rate, we needed to have a large wing, and due to size limitations, that left us with a little space for the vertical stabilizer. So instead of classic stabilizer with an elevator, we designed a stabilator. To counterattack a high pitching moment to the main wing, we used a reverse NEICA 4408 airfoil to balance it out. Using maximum takeoff weight from the mass analysis, we calculated stability and maneuverability neutral points, and we got 7 to 12% stability margin. We also performed a dynamic stability analysis using XFLR 5 software. The plane can dump short period oscillations, fugodoid, roll and dash roll. Pilot's input is needed to exit the spiral, which is not an issue. For structural analysis, we started with choosing the basic materials based on no external factors. Then, we followed an interactive design process to determine geometry, internal loads and stresses. We used a flight envelope to compute loads on each part of the flight and unit loads from steering and gas tank. The maximum load factor is 4.1. Wing and empennage structure was calculated using analytical formulas. As the wing is made of glass and carbon fiber composites, the displacement minimalization was considered.
The wing is a single carbon spar construction with a fiberglass torsion box. Ribs are made of balsa wood with the exception of shrink ribs, which use carbon fiber plywood material. Winglets and blends are made of polystyrene covered in fiberglass to achieve high smoothness of surface. Trailing edges are covered with aluminum foil to increase the stiffness. The stabilator has a single spar with torsion box, both made of balsa wood. Ribs are made of balsa and plywood. The leading and trailing edges are reinforced with balsa board to add stiffness to the structure. Due to low loads, the structure is covered with heat shrinkage foil. The spar has aluminum tubes embedded into itself, which act as a hinge axis. The fin is made of balsa wood, as the torsion box is negligibly low, a spar carries both bending and twisting. The rudder is made of polystyrene foam covered with aluminum tape. The tail boom is manufactured on the steel core. The structure is made of carbon fiber, glass fiber, and balsa wood. The wings, the empennage, and their structure were glued on the PMAA fixers. For fuselage, we use carbon fiber and glass fiber with helix knee layers to prevent buckling. We considered 3 cargo bay variants and decided to load the cargo from the side to allow for easy access to every bag. Loads from the engine and the front wheel are carried by the plywood frames. The main landing gear is made of carbon fiber composite with balsa core. The front gear has 2 wheels to minimize friction and to provide stability over potholes. Rear wheels were selected based on friction tests, and we chose Cavan Superlight 100mm wheels due to their low rolling resistance and high energy absorption. All wooden parts were cut on our milling machine.
At the end, we verified our initial design assumption with a performance analysis. The goal was to achieve a minimal climb rate of 1.8 meter per second. We performed a set of calculations and the climb speed was a bit over our goal, which leaves a safety margin in case the calculation were too optimistic. Our second goal was the horizontal speed, and during the design process we used all measures to minimize the drag by designing winglets or using the elliptical wing. We also performed a turn analysis to determine if our aircraft will be able to turn within the airfield area. And it seems that even the tightest won't be a problem if we keep the bank angle over 20 degrees at our cruise speed. The team also calculated takeoff run length and verified the calculation method using one of our old aircraft. Even allowed us to approximate the takeoff length is in a fraction of the weight.
This year's rules turned out to be quite demanding.
for their aircraft. But we hope that the Mosquito will face this completely new challenge with very good results. This year's project allowed us to gain new knowledge both in designing and management of the projects. Thank you for your attention, and it's time for the proof of flight.
We are Uvigo AirTech, an air design team from Ourense, Spain, that is made up of a total of 27 members from the aerospace engineering, computer engineering, and even business administration law degrees. All of them are located at the University of Vigo and belong to the campus of the city of Ourense. Uvigo AirTech is divided into 5 different departments in order to cover all needs of the project in an organized way. Structural Design Department. They are in charge of designing and simulating the internal structure of the model aircraft, as well as the management of the manufacturing process. Aerodynamics Department. They are responsible for designing the aerodynamic elements of the model, ensuring that the aircraft is capable of lifting the payload. Propulsion and Dynamics Department. This department assessed the electromechanical design and analysis of the given electric motor and propeller pair, and also designed, simulated, and tested the main motor structural mount, as well as the main and rear landing gears. Electronics Department. This department is in charge of designing, maintaining, and implementing the circuits of the model aircraft. Organization and Marketing Department. The members of this department are the ones who organize the team and manage this image. The external surfaces of our drone are made of prepreg carbon fiber. In this way, our team has been able to learn one of the most used manufacturing processes in the aeronautical industry. In relation to the materials, it has been decided that the molds used will be made of aluminum, due to its density, availability, and the advantages it presents at the time of manufacturing in terms of surface finishing and mold treatment needs. When designing the internal structure of the wing, it was decided that in the first half of the semi-wing there should be 2 beams to provide rigidity and stability. These beams go through the middle of each wing and the fuselage. In the central part, a piece printed in PLA has been placed to transmit the loads of the trailing edge beam to the beams that lift the fuselage. Later, we decided on the number and arrangement of the ribs, and ended up choosing a configuration of 8 ribs. The internal aluminum structure and the carbon fiber are glued using reinforcers of fiberglass and epoxy resin. This will be the same in our wings. The skin of the control surfaces is combined with a solid PVC low-density foam core. That needs to be as light as possible, since it will not be under much structural stress. The empennage is divided into 2 semi-stabilizers and an L rudder. To manufacture them, we use 4 molds in which we laminate the intrados and the extrados of each semi-stabilizer. Finally, we cut the surfaces of the L rudder and glue them to a core foam, so the internal structure is the same as the ailerons and flaps. The aerodynamics department started collecting data of similar planes in order to have some numbers to start our calculations. Then, we defined the main parameters of the plane, which will be used by the rest of the team for their own design. Having the knowledge of making an elliptical wing, we went all in and made our empennage also elliptical. Given the competition's box requirements, we made it in VTEL form. This way, we can make it big enough to not reduce our wingspan. When everything was settled, it was time to cut those wings for making the control surfaces. Given the mass of the plane, if we wanted to achieve that 40-meter takeoff, we needed some flaps. They ended up being too big, but they worked great, and we could use them as spoilers at the landing. Our last step was designing a more aerodynamic shape for the cargo container, and, of course, making sure our calculations made a plane that could be easily flown. In regards to the analytical calculations, most of the critical components like the motor and propeller are mandatory and specified by the ACC regulations. They need to be completely understood, and spreadsheets of performance values need to be calculated in order to select the right components. The motor mount design was totally made in the department, and its two main purposes are 1. The obvious, to transfer the thrust to the rest of the structure, and 2. A more technical one, to protect the expensive motor in case of a nose-hard landing or a complete crash. To achieve that second goal, the structure of the mount was designed with a low safety coefficient, enough to endure bursts of higher thrust but easily breakable on impact, which is reinforced by the use of PLA, as it is a fragile material. The fracture and break-in pattern was analyzed to break inwards, inserting the motor in the fuselage instead of exposing it to further impacts. The undercarriage design was also made by the department after numerical testing of stability and ground clearance needs. We finally settled on a tail dragger configuration made of two parts: an aluminum main landing gear and a TPU 3D printed tail landing gear. The tail landing gear was a bit of a struggle, and our first design, which were also made in aluminum, didn't provide the stability needed for the takeoff run, and they even made us abort some takeoffs. So, we decided to experiment on rapid prototyping using 3D printing of TPU, a flexible material, which gave us extremely good results that allow us to rapidly manufacture our own tail gears instead of waiting for external sources to make them for us. The electronics department started defining some design requirements. First of all, we needed components with a great potential and performance, but with the lowest weight possible. One very important point is servo choice. The chosen servos are light and small and with enough torque for adequately moving the surfaces. We also prepared a custom OpenTX program that allows us a correct control of the surfaces. Related to the aileron mechanism, the aileron was placed at the outer side of the wing. Its drive mechanism was designed with an external actuator due to space constraint that reduced movement range, but the servo has to be placed inside the wing to reduce the aerodynamic impact. The flap mechanism is more complex than the aileron or stabilizer 1 due to the rotational axis position. We have to achieve a mechanism that places the rotation axis out of the wing. To do that, we designed two parts, one fixed to the flap surface and another one fixed to the wing. Related to the VTEL mechanism, we place the surface at the fuselage to add minimal weight rearward, and through a long traction bar we can bring movement to the empennage surfaces.
Trencolot's team was founded back in 2006 by a group of students from the Escola Superior de Enginyeria Industrial Aeroespacial y Audiovisual de Terrassa. Its main objective is to design, build, and fly unmanned aerial vehicles. The team has been participating in the Air Cargo Challenge competition since its first international edition back in 2007, and hasn't missed an edition since. For this year's competition, the team is participating with an aircraft we have named Rovelló. Regarding the aerodynamic design of Rovelló, multiple configurations have been considered with different airfoil, wingspan, chord, and torsion distributions. For each configuration, the propulsive system as well as the aerodynamic behavior have been analyzed. With this information of each individual, the main performances have been analyzed. These main performances are those that directly affect the final score of the aircraft: maximum payload, maximum level speed, and maximal vertical speed. Each individual has also been considered for two possible scenarios, with a takeoff distance of 40 meters and a takeoff distance of 60, as these two cases have different treatment in the regulations. Once the result for all cases have been computed, a post-process study has been carried out to compute the score of each individual, considering that all cases participate in the competition. The process has been repeated 3 times to ensure a configuration close to the optimal. In this video, we are laminating the structure of the wing using the previously prepared molds. Before starting the epoxy mix, it is necessary to check that all the components are ready and they all fit where they have to. It has to be remarked that the conditions were really harsh. We were over 36 degrees, and at that temperature not only the physical effect is high, but the epoxy hardens much quicker, so no time can be lost. Once it is done, we mix the epoxy with the hardener and start laminating. The wing is composed of a carbon fiber sandwich. Once the 2 layers of carbon fiber have been laminated, the spar caps and the flap hinges have to be added. Next, perforated film and breather are added, and finally the vacuum bag is set. It is critical that no links are present, as the results directly depend on the quality of the vacuum. Once the epoxy is fully cured, the mold can be taken out of the oven and the breather and vacuum bag can be removed. Next, the upper and lower surfaces have to be glued together. To do so, the spar core and some ribs have to be added in order to keep the structural strength of the wing. The main spar of the wing is made out of a composite sandwich made out of carbon fiber, royal and wood, with the carbon fiber being embedded in the structural skin of the wing during the lamination process, and the wood being placed at either side of the royal nucleus. Once the upper and lower surface of each wing segment have been joined and glued together, there is some post-process to do. The edges have to be polished to ensure a smooth landing edge and also to ensure that the segments are safe to handle without risks. Then the ailerons have to be set. This includes the preparation of the hinge, preparing the location of the servos, and finally setting up the electronics.
So the electric and electronic system of the plane is actually quite simple. It consists of two systems. The first one being powered by two main batteries connected in parallel. They are 3S and they feed directly into the powertrain. We have decided not to use the BC integrated in the ESC because it's more unreliable, and we have a single signal wire running from the ESC to the receiver so we can control thrust. Then the secondary system is the one that we use to power the receiver and the servos. In case there's a power cut from the main train or any emergency, we can still have control of the plane. And as you can see, it's a smaller 3S battery that feeds into a BEC, and this BEC has two outputs with step-down voltage. The first output we use to power the servos on the tail and the receiver, and also the other output is the one that controls the servos on the wingtips, so we can move the flaperons efficiently. And the wires travel through the inside carbon rods of the fuselage and through the inside of the wings and go directly into the top of the cargo bay where the receiver and batteries are located.
In the first flight, the aircraft is capable of taking off, but dynamic instabilities appear due to bad location of the center of gravity. The windy conditions do not help either. Second day, the aircraft is longitudinally stable, but it lacks some lateral stability to the cargo bay as it isn't covered yet.
Hi, I am Yuri and I am the team leader of the Leaning project.
Hi, I'm Federico and I'm attending the Bachelor in Aerospace Engineering. As a member of the team, my role was to create and place in the best way possible the electronic system. And in addition, also to help developing the CAD 3D model.
Hi, I am Geraldina. I'm attending a Master in Aeronautical Engineering, and my role as a member of the team has concerned the design of the model aircraft from the aerodynamic point of view.
Hi, I'm Eduardo, and I'm attending the Bachelor in Aerospace Engineering. In the team, I was in charge of helping the CAD and the electronic system design.
Hi, my name is Ivan. I'm an aerospace engineering student at the University of Pisa and I'm a member of the team Leaning project. In Leaning project, I helped designing the main structural components of the aircraft and performing the relevant finite elements analysis.
Hi, I'm Domenico and I'm attending the Bachelor of Aerospace Engineering at the University of Pisa. For the team, I've created almost all CAD components and manage the graphics and video realization.
Hi, my name is Claudio. I'm waiting the Bachelor of Aerospace Engineering and I help my team to making the development of mechanical structure and design in SolidWorks.
My name is Luca. I'm an aeronautical engineer student and I'm part of the aerodynamics area of the team.
We are a recently born team and we faced so many challenges even before the challenge. During the pandemic period, we make a strong effort to keep us together and do our best. Even when we broke some parts, we learn and keep going. This is the real first step for every engineering project. Starting from this experience, we look forward to grow up stronger and make much improvements. We take some specific decisions on wing shape and aircraft dimension correlated to the expected payload prediction and aircraft performance. We faced with our supplier to make our idea real, with many technical challenges to resolve. For example, draft angle, minimum thickness and material specifications and so on. As we say in tech report, the maximum geometric envelope drives us in the design, and we thought that cargo bay in a ogive shape, it would be the right choice. But during the test we had many issues regarding the structure and dynamics of the aircraft. We learned so much and we tried to fix it as it possible. Probably we asked too much in terms of weight, speed for our design, and we should have designed our cargo bay for less payload in order to have an aircraft easy to control. But anyway, as I said before, we are a recently born team and we consider this as a good start for our next challenge.
Regarding flight mechanics, I was involved in studying the main characteristics of the aircraft, such as weight distributions and stability margins. The determination of aerodynamic derivatives was quite challenging at the beginning because we weren't sure about the reliability of our numerical code, and we had to use our experimental flight tests to confirm the results.
After choosing a configuration, we ran several CFD analyses in order to compare the results with those obtained before analytically and to validate the chosen configuration. I think this part has been very important, both because it has allowed us to get in touch with softwares that are very important and that we had never used before, and because it has helped us to understand the limits of the mathematical model that we've used for this analysis. As a matter of fact, I think that there's a big difference, or better, there might be a big difference between the hypothetical behavior of a machine and the actual behavior of this machine. And during this part of the job, we've really understood this issue?
One of the biggest challenges for our team has been the choice of the design of the wing and the tail of our airplane. And for the wing, we choose a simple rectangular wing because we wanted to increase the lift. And the choice of using a T-tail comes from consideration about the downwash angle instead. The experience has been very stimulating because it's given us the chance to turn into reality the knowledge we have learned during these years in the university.
For modeling our aircraft, we relied to SolidWorks Corporation that give to us full licenses of their software and become our sponsor. Using CAD software, we modeled all components and simulated the assembly between them that was essential for the subsequent construction.
During the test phase, we encountered some problems. In the beginning, the takeoff was not perfect, and we had some problems in making a stable flight. The first tries are always the most uncertain. Different unfortunate crashes led us to the necessity of substituting or even rethinking some parts. Cargo bay and components of the landing gear were between these parts. Also, we retained safer to change the fuselage pipes. 3D printing, pieces deliveries, and mounting on our model required time, while we were trying our best to make the flight the more stable possible. In the end, after all the tests, we were able to carry out stable flights, and now we can say that our model is finally ready for the competition.
Good day everyone, I'm Otto Harkari, the team leader of Team Albatross, and this will be a presentation about the design and manufacturing process of the blended wing 3.7 concept. And here you can see our team. I am the guy on the lower right corner, and this is obviously the time of the coronavirus because we all have our masks on. But about the team, we are all students of Tampere University, which is a university in central Finland. Our team composition has changed a little bit during the competition because of the elongation of the competition. Our team is divided into groups. The groups are aerodynamics, structural design, techniques, building, promotion and finance. And we had to merge a little of those groups together because of the changes in the composition of our team. In this slide we have some better pictures without the masks of our individuals. So I'm the one on the left upper corner. I'm the team leader of the team Albatross. I have background in mechanical engineering and I'm minoring in aeronautical engineering. In our university we always have to take, if we want to take aeronautical engineering, we have to take mechanical engineering as a major in bachelor's phase, and then we can take the minor in aeronautical engineering, and in the master's phase we can major in aeronautical engineering. So that's my background. Mechanical engineering and minor in aeronautical engineering. I'm an experienced aviator and an airline pilot, and I haven't built model airplanes before this competition. Then we have Sami, who's are responsible for the finance of the team. He's an automated engineering student, and in contrast to me, he is an experienced model aircraft building, and he also participated in Air Cargo Challenge 2019. Then on the lower left corner we have Akseli. He's soon graduating in the aeronautical engineering major, so he's graduating from the master's phase. And Akseli is responsible for the aerodynamic design of the aircraft, and we can perhaps say that Akseli has done all the aerodynamic design of the aircraft. So he played, or he is playing a very big role in the team. Akseli hasn't built airplanes, model airplanes before, and he's an enthusiastic and experienced aircraft designer and has worked in companies as an aircraft engineer. Aro is or has the same background as I have, and he's continuing to the masters in aeronautical engineering. He's responsible of promotion in our team, and also commercial pilot and a flight instructor, currently working as one right now. He hasn't built model airplanes before. Right, in this slide on the left upper corner there is Jouko, who also has quite of the same background as I and Aro have. He's a mechanical engineering student with minor in aeronautical engineering, and he's also beginning masters in aeronautical engineering in Tampere University. He hasn't built much model airplanes before, but he is a very experienced simulation software developer and also a general aviation pilot. Then on the upper right corner, there is our pilot for the competition, Lauri. Lauri is an electrical engineering student, and he is responsible for aircraft building. And I believe that he is actually currently building the aircraft as I prepare the slides here. He is very experienced in model aircraft building and piloting, and he also participated in a Cargo Challenge 2019. On the lower left corner, there is Juho. Juho is soon graduating from the aeronautical engineering field as a master. and he is an experienced model aircraft builder, and he participated the Air Cargo Challenge 2019 as well. Team, I am the guy on